In this video, we will learn how to derive appropriate shape functions for beam elements that can be used to specify Vx for use in the elastic strain energy equation derived in the previous video. Recall from our previous video that the strain energy for a beam is given by lambda E equal to EI times by the integral over the length of the element multiplied by the curvature, all squared with respect to dx. Our first priority, before attempting to evaluate this integral, is to specify an appropriate form of Vx via the finite element process. The governing differential equation for a beam is given by the following fourth order differential equation. d4v by dx4 is equal to Wx, where Wx is a distributed load term. Let us remind ourselves of what a beam bending element looks like. The displacement u2i minus 1 u2i at node I, u2j minus 1 and u2j at node j. The element has an overall length of L and coordinate axes y and x. If we now draw this element in a slightly deformed configuration, just to emphasize some of its shape, then at each end we can draw the boundary conditions. So at end I, 0, we have v of 0, and we have a rotation dv of 0 with respect to dx, and at end L we have a displacement v of L and a rotation dv of L by dx. From looking at this diagram, the following boundary conditions must be satisfied. V of 0 must equal u2i minus 1. The rotation dv of 0 by dx must equal u2i. The displacement L must equal u2j minus 1. And the rotation at L must equal u2j. Because we are only interested in what's happening at the nodes, we can neglect the uniformly distributed load term Wx in equation 2. So the governing differential equation is now written as d4v by dx4 equal to 0. A general mathematical form for Vx that will allow the boundary conditions to be satisfied is given by the following. V of x is equal to a1 plus a2x plus a3x squared plus a4x cubed. We note that the derivative of this with respect to x is given by a2 plus 2a3 times by x plus 3a4 times by x squared. As with axial force elements, the coefficients a1 to a4 need to be determined. This can be done by evaluating Vx at the boundaries. For coefficients a1 and a2, this can be done easily, simply by substituting in values of x equal to 0 in equation 8 and equation 9 for displacement and rotation respectively. So, v of naught is simply just equal to a1, and we know also that v of naught must equal, as we stated up here, u2 of I minus 1. So we can say that a1 is equal to u2i minus 1. Similarly, the rotation at x equal to 0 is given by a2, and this is equal to u2 of I, as we can see here. So we can say that a2 is equal to u2i. a3 and a4 need to be determined simultaneously. If we write down expressions for VL and dVL by dx, we can see that they are a pair of simultaneous equations. VL is equal to a1 plus a2L plus a3L squared plus a4L cubed. dV of L by dx is equal to a2 plus 2a3 times by L plus 3a4 times by L squared. V of L is equal to u2j minus 1, and dVL by dx is equal to u2j. We know that a1 is equal to u2i minus 1, as we've just determined. We also know that a2 is equal to u2i. So we can substitute these values for a1 and a2 into equations 11 and rearrange to get the following. u2j minus 1 minus u2i minus 1 minus u2i times by L is equal to a3 times by L squared plus a4 times by L cubed. u2j minus u2i is equal to 2 times a3 times by L plus 3a4 times by L squared. We can then write this in matrix vector form so that we get u2j minus 1 minus u2i minus 1 minus u2i times by L, u2j minus u2i, and that's equal to the matrix L squared, L cubed, 2L, 3l squared, all times by the vector containing a3 and a4. Solving this 2 by 2 system gives us values for a3 and a4. So we have 1 over L4, L to the power of 4, times by 3L squared minus L cubed minus 2L, L squared, times by U2j minus 1 minus U2i minus 1 minus U2i times by L, U2j minus U2i. We now need to expand and simplify this equation. So firstly, let's simplify the matrix to get 3 over L squared minus 1 over L minus 2 over L cubed 1 over L squared times by U2j minus 1 minus U2i minus 1 minus U2i times by L, U2j minus U2i, and that allows us to obtain A3 and A4. So multiplying this out, firstly for A3, we have A3 being equal to 3 over L squared times by U2j minus 1 minus U2i minus 1 minus U2i times by L, and then also minus 1 over L times by U2j minus U2i. Simplifying this and collecting the terms, we have 3 over L squared U2j minus 1 minus 3 over L squared U2i minus 1 minus 3 over L U2i minus U2j over L plus U2i over L. Finally, this gives us 3 over L squared U2j minus 1 minus U2i minus 1 minus 1 over L times by U2i plus U2j. Similarly, for A4, we have minus 2 over L cubed times by U2j minus 1 minus U2i minus 1 minus U2i times by L plus 1 over L squared U2j minus U2i. That's then equal to minus 2 over L cubed U2j minus 1 plus 2 times U2i minus 1 over L cubed plus 2 times U2i over L squared plus u2j over L squared minus u2i over L squared. Finally, that's equal to 2 over L cubed times by u2i minus 1 minus u2j minus 1 plus 1 over L squared u2i plus u2j. The reason for these algebraic manipulations is that I wanted to collect similar coefficient terms here for subsequent manipulation. We now substitute our values for a1, a2, a3 and a4 back into our function v of x. So now v of x is equal to u2i minus 1 plus u2i times by x, that's a1 and a2, and now the terms that we've derived just a second ago, plus 3 over L squared times by u2j minus 1 minus u2i minus 1 minus 1 over L times by 2 u2i plus u2j, and this is all times by x squared because this is the a3 term, plus 2 over L cubed times by u2i minus 1 minus u2j minus 1 plus 1 over L squared u2i plus u2j, and this is all times by x cubed. So, just as a reminder, this is a1, this is a2, this is a3, and this is a4. So you've now determined what these are. We just need to tidy up the mathematics a little bit. So we can collect coefficients of u2i minus 1, u2i, u2j minus 1, and u2j. So this gives us v of x equal to u2i minus 1 minus 3 over L squared u2i minus 1 times by x squared plus 2 over L cubed u2i minus 1 times by x cubed plus u2i times by x minus 2 over L u2i times by x squared plus 1 over L squared times by u2i times by x cubed plus 3 over L squared times by u2i minus 1 times by x squared minus 2 over L cubed times by u2j minus 1 times by x cubed minus 1 over L times by u2j times by x squared plus 1 over L squared times by u2j times by x cubed. So you can see here that we've collected terms for u2i minus 1 in this row, u2i in this row, u2j minus 1 in this row, and u2j in this row. We're now in a position to say that v of x is equal to 1 minus 3 over L squared times by x squared plus 2 over L cubed times by x cubed, all times by u2i minus 1 plus x minus 2 over L times by x squared plus 1 over L squared times by x cubed, all times by u2i, plus 3 over L squared times by x squared minus 2 over L cubed times by x cubed times by u2j minus 1 plus 1 over L times by x cubed minus 1 over L times by x squared, and this is times by u2j. In these equations, we can call these terms in brackets the shape functions. So this would be called shape function n2i minus 1. This would be shape function n2i. This would be shape function n2j minus 1. And this would be shape function n2j. The displacement equation is now expressed in terms of the nodal displacements and corresponding shape functions. So we can write v of x in the following form: n2i minus 1 times by u2i minus 1 plus n2i times by u2i plus n2j minus 1 times by u2j minus 1 plus n2j times by u2j. We can then convert this into a matrix: n2i minus 1, n2i, n2j minus 1, n2j, times by our element vector ue for displacements, which again